Sir, we can start now. There is some
एक मिनट वहाँ से
time
रिकॉर्डिंग
delay
कर दोगे क्या?
between the live streaming and
टीम्स
this
में
one.
टीम्स में सर को बोल दो
करीबी है।
Hello.
एक बार यूट्यूब पे भी चेक करना, आवाज आ रही है उसमें?
Okay, you want
Yes.
me to start?
Yeah. Just hold on, sir. I will give the brief introduction. Then we can start. Agrawal, sir, we can
Okay,
start.
sounds good.
Yeah, please go ahead.
Yes. So sorry for the delay in this popular lecture on National Science Day. So we are honored to have with us Professor Victor R. Baker, GSA Distinguished International Scholar and Regent Professor from the University of Arizona. So today we celebrate our National Science Day in celebration of Raman effects by Professor C.V. Raman, the Nobel laureate from India, in 28th February 1928. So our request was accepted by Professor Victor, and I'll just read his brief biography, although he does not require any introduction. But for the benefit of our members, I will just briefly read his biography. Professor Victor is a Regents Professor of Hydrology and Water Resources and Geosciences and Planetary Sciences in University of Arizona. He received his BS in Geology from Rensselaer Polytechnic Institute in 1967 and the PhD in Geology from University of Colorado in 1971. He has authored and co-authored more than 360 research articles and 16 books on the topics of paleo-flood hydrology, flood geomorphology, channels, valleys, geomorphic features of Mars, Venus, and catastrophic Paleocene floods in northwestern US and Central Asia. He has also published work in history, philosophy of Earth and planetary sciences, and interface between environmental science and public policy. Professor Baker has been president of Geological Society of India in 1998, chair of American Association of Advancement section in Geology and Geography from 92-93 and 2008-2009. He has also served as a president of International Union of Quaternary Research Commission on Global Continental Paleohydrology from 1995 to 99. He is also member of many prestigious science academy, to name a few: Polish Science Academy, Honorary Fellowship of European Union of Geoscience, David Lytton Award for the British Society of Geomorphology, and Distinguished Scientist Award and Distinguished Career Award from the Geological Society of America in the Quaternary Geology and Geomorphology Division. He is also Fulbright, his senior research fellowship, Indo-American Fellowship, and Sir has told that he has visited the National Institute of Hydrology during 80s during one of the first visit to India. And His work on the mega floods has been featured in many public media, for example, in multiple television documentaries in PBS and BBC, and also National Geographic and Discovery Channel. And also, he has made 2005 Nova production Mystery of Mega Floods. So, we are truly honored with your presence, Professor Baker, and I have been following your work, whether it is terrestrial floods on Earth or on Mars. And recently, while reading your editorial preface in the book Lakes of Mars, so I was really impressed the way you present the traditional aspect of science as well as the awe and wonder what you have described in your own words. So it is really honor for us to listen to your experience and the thoughts on this exciting topic for senior researchers as well as the younger generation, which can learn some little bit from your knowledge. So floor is yours, sir.
Okay, thank you very much. This is my favorite topic, really big, giant floods. The scene on the left shows some of the extinct animals that lived in what's now the United States about 20,000 years ago in the last ice age. And the large mammoth is escaping a giant flood in the background. These waters coming across part of the northwestern United States were 100 meters or 200 meters deep and very high energy. I'll be talking more about them. On the right is a depiction of Mars, the surface of Mars, with high elevations in the red color, low elevations in the blue. And shown is the pattern of great channels that developed because of flooding on Mars about 3.5 billion years ago. And these channels went from the cratered uplands, which are shown over most of the surface, up toward the top part shown in blue, where there was a large water body. So I'll talk about both of these and then talk about how this relates to the kinds of floods that occur today and are pose problems for human beings. Now, throughout the history of humankind, there have been myths or stories in ancient societies about great floods. And usually these stories will say that the whole world that these people lived in was inundated by vast floods of water. So this map shows in the dots some of the places where these stories have taken place. And I think that some of these floods may have occurred to people living at the end of the last ice age when there were giant mega floods on the earth. So what is a mega flood? This term, which I helped describe, refers to a tremendous flow of water on the land where the quantity of water per unit time, the discharge, is measured by the same units as ocean currents. So when we have an ocean current like the Gulf Stream in the Atlantic, the unit of measure is a sphere drip, 1 million cubic meters per second. Now, ocean currents move very slowly, but the mega floods that have occurred on the land are very fast. And shown in the map in red are locations where these giant floods occurred mainly during the last ice age, about 20,000 years ago. And you'll see that there are many in the northern continents because that's where there were giant ice sheets. You'll see that there's quite a large number of these, and more have been discovered all the time. Many people don't know about these floods,
Professor, excuse
even
me.
though they have
Professor
occurred.
Victor. Professor, it seems your screen
Yes,
we cannot see now.
my screen can't be seen.
Yeah, we cannot see.
What should I
Uh,
do? I can escape
you can
and
share again.
go back.
Yes, share
Yes.
again.
Can I share again? Okay, I'm not sure where I do that. It says that I am sharing the screen right now.
Yeah, but Praveen, can you see the screen?
It says I pulled up and it said I am sharing. I'm looking at a thing that tells me to stop sharing, but let's see.
Hello.
Okay, now I'm looking. Now I'm looking at you, and
No, we cannot. We cannot see your screen now.
Yeah, only voice is audible.
only what's available.
What your voice is audible, not the screen. It is actually fixed at the front page. So you can unshare and share again.
Okay, just a minute. Okay, I stop.
Yes.
Now I will go to entire screen. Okay, so is that bringing up the screen? Can you see the screen now?
Not yet.
No. It's saying that I am saying that on my thing it says I am sharing, and recording has started. I don't know what has happened.
can you forward your presentation to me by email? So I will try to present from here.
Maybe a very large file. That's the problem.
Yeah. So in my
Um,
Gmail you can forward it, or in my this uh, Hotmail.
yeah, but I don't know if I can send it as an attachment because it's a very large file. Well,
Yeah.
I can see you, and I don't know why mine is not sharing. Let me try this again. And it says allow it to be seen, and I put on allow, and it says I'm sharing my screen,
Yeah, but it's
but you're not
white,
seeing it.
white is coming. Only the white.
Just white.
Yes. So you can just log off once and then join again. Maybe it will sort out.
Join the meeting again.
Yeah, just leave and then join again with the link.
Okay, I'll stop.
This red button. Yes.
I've reconnected. Can you hear me?
Yes.
Okay, I've reconnected. And I will share screen again.
Your
Okay.
your video is not coming. I don't know why. Earlier it was coming.
So I've reset everything. It says that I'm sharing. I see you, and you see me.
No.
Yeah, I see everybody on here, and it says that I am sharing. My mic is open, camera, everything. Okay. I don't know. Maybe it timed out, but okay. I see you're muted, Praveen. So you're muted.
Can you send the slides, because I'm not sure we are able to see you. You just
The file may be too large for me to send the slides. That's the problem.
okay. Just hold on. Teams.
I don't understand because we were seeing them before easily.
Yes,
Maybe
yes.
the time is maybe the problem that it took so long. But we started the whole thing again, and
Yes.
should be working.
Yeah. So just hold on. I'm sharing the new link.
Okay, there's a new link. Okay, I'll go back and connect again.
No, 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 no. I'm sending the Teams
Oh, okay.
this Google link.
Oh, okay.
Just hold on. You change it. I have given in the chat box. So you open this Google Teams in the message.
Yes.
This is the Google Meets link.
Okay. So I should go to a new link.
Yes.
Okay. Okay. I'll have to go to. I'll close out of this one and look for a new link.
Yes.
Okay. Yeah. Okay.
So you can join this link.
चैट में डाल दीजिए वो लिंक।
चैट में डाला हुआ है ना।
हमें शो नहीं हो रहा है। सबको फिर वहीं पे ज्वाइन करना पड़ेगा उसमें।
फिर हमको भी ज्वाइन करना पड़ेगा ना, अदरवाइज हमें कैसे पता चलेगा? फिर वो यूट्यूब से लिंक हो जाएगी, नई लिंक। हमको भी तो फिर दोबारा ज्वाइन करना पड़ेगा। अनम्यूट करो, अनम्यूट करो।
आपने मेल कर दिया जीमेल में।
तो मुझे अभी लीव करके दोबारा उसमें ज्वाइन करूं?
हाँ सर, हाँ सर।
मेल करो।
क्या है यार, हमारे है सर इसमें
ये से बोलो ना।
ये खोला तो है, तुम बताओ ना जीमेल। किसे कर रहे हैं सर? करके ले आओ, हो जाएगा काम।
स्क्रीन उस पे यूट्यूब पे।
Hello.
Hello?
Yes, yes. So I think it is much easier now. So you simply share the screen now, present now.
Okay. Now, yeah, sorry, it took a while to get the message. Now, where is the share screen?
There is a hand, left side of the hand icon. Share now.
icon.
To the left of the
One arrow is
okay.
there, box and arrow.
Yeah, I see. Okay, so I go to entire screen. Okay, so is that, do you see now? Do I press allow?
Yes.
Okay. Okay, it says I'm sharing.
Yes. So
Okay,
you
can you
can,
see the talk?
yeah, you can go to the first slide.
Okay. Well, so you didn't see any slide before?
Yes, only voice was there, so we can go to the first
Oh, I
slide.
see. Okay. Okay.
Yeah.
So,
Yeah.
so now you see the first slide. Oh,
No, I
just
think
a
you
minute.
have.
You
Yeah,
can keep, yeah, yeah, yeah.
Can you
Okay.
next slide, please?
Okay. Yep.
Yes.
Yeah,
Yeah.
perfect. Now it is
So
perfect.
this is the location of the various flood stories from ancient people around the world. Many examples of flood stories, and some of these people may actually have seen the true mega floods that occurred during the last ice age around 20,000 to 16,000 years ago.
Yeah.
So this term mega flood, which I contributed to the discussion of this particular term, these are flows of fresh water on the land that are measured by the same units as ocean currents. Ocean currents being very slow movements of water, maybe 1 meter per second. But mega floods are much faster, moving at tens of meters per second. And these mega floods are associated with special conditions that occurred around the giant ice sheets. They're measured in millions of cubic meters per second. Many people don't realize that there's evidence of these mega floods near where they live. And I'm going to show you one example. Here, the islands of Britain separated from France, and the channel that separates them was created by mega flooding. Here are some images made from bathymetry of the ocean floor through the channel. And you see at the bottom, the location. These data were unknown until about 20 years ago because the topography of the sea bottom was a Cold War secret. And it was only relatively recently that information became available. Shown in the dark pattern is the pattern of flood carved channelways that are on the floor of the channel. And this pattern we call anastomosing. It consists of higher areas shown at the top in green and deeper areas shown in blue. These look like islands, but they were actually created by the character, but also very deep through the channel. So this gives some idea of the scale of the mega flooding and the general pattern that we see in mega floods, both from Earth and from Mars. So the map on the left is a polar view of the Earth during the last ice age at the peak, when the area in the light blue shows the distribution of glaciers. The area in purple are giant lakes that formed around the margins of the giant ice sheets. And the red arrows are megaflood zones, that where there was flooding that emanated out from the glacier areas. These floods were caused in different ways, and I can't explain all of them, but there, as you can see, there were a great many. And in the upper right, you see Asia at the center, Shown in the light blue are some of the same giant lakes you see at the left. And you see that in the arrows, both the red and the yellow, zones where mega flooding occurred. You can see that in South Asia, the Indus, the Ganges, the Brahmaputra, these all had mega floods that were sourced from the Himalaya. So I'm going to talk about the area I worked most in, which is the northwestern United States. But it is only a small part of the area impacted by mega floods during the last ice age. So shown in the blue hatcher areas are the big ice sheets as they were melting back after their peak around 20,000 years ago. And the arrows are zones where there were great mega floods. These floods carried immense amounts of sediment out into the adjacent ocean basins. So those areas are shown in pink. And the one I will talk about next is in the left center. I don't know if the arrow shows up that I'm on my screen, but it's basically just to the south of the big ice sheet called the Cordilleran ice sheet. And it extends out to the area number 4. Most of the sediment was deposited out in the sea, but the area of erosion was occurring on the land right near the ice sheet. And the next image will show some detail of that area. So here is a portion of the northwestern United States. Canada is at the top. And you can see in blue the areas that were covered by glacial ice about 18,000 years ago. In yellow is the area that was affected by the mega flooding. And in blue, light blue are the giant lakes. The mega flooding that occurred in Washington state in the Northwest created a landscape known as the channeled scabland. And it is a great anastomosing complex of eroded channels. And the features in this landscape are typical features that we see in mega flooding in other parts of the world. And similar things occur also on the planet Mars. That's one way we were able to discover that these occurred on Mars. So these include giant gravel bars. And you see in the upper left, there's a road that cuts across this one. This gravel bar is maybe 1.5 kilometers long. In the right is a giant cataract. These cliffs are hundreds of meters high, and they resulted from ponded water at the top of the scene flowing over a edge of cliffs and eroding back, somewhat like a waterfall, but unlike a waterfall, the water was as deep or deeper than the lip of the cliff that forms at the head of the cataract. Shown in the lower left is what was called scabland. These are big rock basins. The little white line that is near the left center, that is a road. And so these rock basins are as much as 100 meters across that were scoured into basalt bedrock. And on the lower right is a streamlined hill of sediment. Actually, it was a wind-deposited sediment called loess that was eroded into that streamlined shape by the catastrophic flood water. So in the map at the bottom of this image is this area that is called the channeled scabland. Shown in the sort of pink color is the area that was covered by this loess, and then the eroded areas that were cut into the underlying basalt bedrock are where the arrows are located. That's where the flooding came across the landscape. And you can see this pattern called anastomosing, where there's flood pathways that divide and reconverge, and they sort of stream across the landscape, following what was the previous river valleys that dissected that landscape. Now, when I began studying this in the 1970s, it was possible to calculate the magnitudes and the physics of the flooding because one can reconstruct the elevations of the water shown at the top on profiles that cut through the landscape. And the slope, the fall per unit distance of the water surface that's reconstructed is proportional to the energy of the floodwater, because that determines the velocity with which the water flows over. So my work began as a quantification of the flood process, calculating such things as the bed shear stress and the rate of energy expenditure on the bed of flow. And what I found that the character of the flow is incredibly more powerful than a normal river. So in the diagram in the lower right, you see these measures of the stress of the water across the bed, and on the right side, the velocity in meters per second. And a typical big river like the Mississippi or the Amazon or the Brahmaputra, the water flow velocities, even in floods, are no more than 1 or a few meters per second. But in the catastrophic floods, the water flows can be approach 100 meters per second. The water can be moving as fast as speeding automobiles on a major highway. And that, because the energy is proportional to the velocity squared, the energy levels in these floods are astronomical. In the upper right is a particle of bed load that was probably also in suspension. So you can see from the vehicle that's just off on the right that this thing is maybe 20 meters across. And all of these large boulders in the foreground, they're smaller, but they're as large as this automobile that's off on the right of the picture. So these flows were mind-boggling in their characteristics. Also shown here are giant dunes. They're in fluvial geomorphology, we call these dunes, but they're not made of sand and they weren't formed by wind. You can see through the center of the picture a road. So that's the size of a vehicle. The spacing on these ripple marks is about 100 to 150 meters. And there are boulders a meter or two in diameter on the surface of these, and they're composed of coarse gravel, not sand. They were produced by the floodwater that came down through this extremely large channel. And here's another picture of that giant boulder. This is merely to show you that the energy that is in these flood flows was incredibly great. There's nothing like this occurs on the Earth today, and there were special circumstances that allowed this to happen. The water that was released from the ice-dammed lake that I showed in the earlier picture was 800 meters deep when the ice failed and allowed the water to begin to flow across the landscape. 800 meters. The potential energy is proportional to the to the depth of the water where it was released. And that potential energy all got transferred into kinetic energy. And that's why the energy levels are so high in these giant megafloods. But those aren't the biggest floods that have ever happened. The biggest floods that are known were not discovered until the early 1970s, when we began to get images of the surface of the planet Mars. So this is a diagram I published in the journal Nature a number of years ago that compares the channel cross sections of various rivers and channels. So down in the lower right, you see the Amazon River, the biggest river on Earth. And to the left center, you see one of the channels from the channeled scabland. If you go up, you see the width and the depth. There's an exaggeration scale on the depth. So on this one, you have about 100 to 200 meters deep. That is the English Channel. And then at the middle is the Strait of Gibraltar, separates Spain from North Africa. That was carved 5 million years ago by a giant mega flood, but it was salt water. It was where the Atlantic Ocean spilled into the then dry Mediterranean Sea. That is the largest mega flood channel we know of on Earth, but it's a little different than the ones I've been talking about. The channels above that, the cross sections, are from Mars, and one of the biggest ones on Mars is this one called Passai. So here is a diagram showing the relationships of some of the giant channels on Mars. That picture I showed near the beginning had the cratered terrain, which is in the southern part of Mars, and it showed flows that went to the northern part, which became a zone of ponded water that we have termed Oceanus Borealis. Now remember, these channels formed 3.5 billion years ago. Mars is a very different planet today, but in its ancient past, it had an incredible amount of water on its surface. And that Kasai channel, which is about 2,500 kilometers long, is the one near the center here. And you notice these large channels are directed toward this low-lying basin at the northern part of Mars. So here is a detailed imagery showing topography. This was produced from a satellite called the Mars Global Surveyor that had laser altimetry that was able to make a rendition of the topography. So you see that in the higher elevation areas shown in the yellow, there's a zone with more craters on it, and the channeling of Kasai Vallis is cut into that. You see these streamlined elements and the anastomosing pattern of the channels that are cut into this higher surface. This is what I said is a characteristic of large megafloods. To give you a scale, the width of this channeled area at the top is about a couple of hundred kilometers, maybe up to 400 kilometers across. So this is incredibly large, involving immense amounts of water. This is the same area in more detail, shown with a little more accentuation of the anastomosing pattern, the streamlining, and the elements on the landscape. This old landscape of Mars was heavily cratered. Those craters formed in what's called the late heavy bombardment of the solar system that occurred about 4 to 3.5 billion years ago. So that ancient landscape was carved by these giant floods. So here's backing off a bit. The area that I was just showing is up near the top. It's this area here. That's the same zone. That's about 400 kilometers across. But you see that there's many other large channels labeled J and S and T and A, W up here. And they all are directed toward the low-lying area shown in blue from these higher areas shown in red. That another aspect of these is this sort of blocky looking material called chaotic terrain. And what this is showing is that the water that formed these channels was emerging out of the subsurface of Mars. So they've been termed outflow channels. That Mars was exceedingly rich in water in its subsurface. And as the water flowed out, there was collapsing occurring on that surface, making this chaotic terrain. But we can get an idea of the quantities of water by this streamlining, and you should see it extends out into these low-lying areas. And now the next image is going to look back at Kasai Vallis from the northern plains of Mars. So this is just an image, and Kasai is at the bottom, and you see these other big channel ways that are coming out. Now remember, this Kasai Vallis is 2,500 kilometers or so long and about 400 kilometers wide. So this is an incredible big scale. And then this big low-lying area on the northern part contained a water body called the Oceanus Borealis that was fed by these immense channels. Now, when I first started writing about these in the 1970s, some of my colleagues said, well, why are there no deltas at the mouths of these channels? You notice there's no delta. There's no delta at the mouth of the Columbia River in the United States because megafloods don't leave deltas. The sediment is out into the ocean basin and spread all over the ocean basin. This is a product of the high energy of the flows. Deltas there's no delta can form. Deltas form where the energy drops off and the sediment is dropped. These floods are coming in at tens of meters per second. So there's no way to drop even very coarse material. It flowed out across the whole northern plains of Mars. Okay, so you may be asking, what does this have to do with floods that might affect people? Yeah, in this cartoon, this was made about the time we were talking about the floods on Mars. Here you see a little Martian coming asking for some money to help with the sad conditions on Mars 3.5 billion years ago. That's just a bit of humor because these kinds of floods were occurring on another planet. It doesn't have anything to do with what's going on Earth. Do we have anything like that on Earth? Here is a flood. This occurred in Japan. It occurred in 2011. This flood was produced from the sea. It is the Tohoku Oki tsunami. And that water was about 20 meters deep. And you can see that it is carrying houses, cars, incredible amount of debris, and destroying everything in its path as it flowed across. It flowed across this is in the northern eastern part of the island of Honshu, the largest island in Japan. This came across a city, and there's the city after the tsunami passed over it. All you see, except for these very heavily constructed concrete buildings, you see that the houses were just completely swept away. This was, and you see the effects of the flooding all around the adjacent hillside. This is a wet area, wet climate, and this. My Japanese colleague said that the effects of the tsunami looked like Hiroshima after the nuclear bomb. Things were just completely swept away. So we do have catastrophes on the Earth that, although not of the scale that we had in the past, nevertheless, the energy can be produced in a similar kind of way. Here's a couple of my colleagues from when I was in the field studying this. In fact, the fellow on the left is one of my PhD students. And you can see the depth of the water that was coming into this area because this bus was floated at the top of the water flow that was coming across the land in that, as in that earlier picture. And it was set down on top of this building. So that gives another indication of the magnitude of the flow. Here is a place where the Japanese had spent a huge amount of money to protect against tsunami waves. This town of Minami Sanriku, fairly large town with some big buildings and structures that were made to be the safety for people to escape the problem of a tsunami. So they had sirens that would go off if an earthquake occurred, as it did in 2011, off of Japan. And people were to go to the top of this structure to be safe from the tsunami wave. They also built this kind of massive wall that would protect the buildings from the tsunami wave that hit this wall. You can see how high the wall is. In the lower right, you see what, when the tsunami wave went over the top of that wall, it was more energetic than it would have been. It exceeded the protection level of the wall, and it was far more destructive as a result of that. And that's what the town looked like on the other side of that protective wall. Here in the upper right is a picture of some of the early parts of the wave when the wave was coming into the town. And in the lower left is the people that were on top of that protective structure. The people that you see in the water all were killed. In fact, everybody on that structure that was 3 stories high, except the people on this pole. There are 2 people that climbed a radio tower on top of the structure, and they survived the tsunami. But the rest of the people didn't survive. There's a close-up of that scene. So this was designed at great expense to help people be safe from this tsunami, and it didn't work. So the Tohoku earthquake and tsunami, the whole story of it hasn't been told. About 20,000 people were killed, many more injured. But the big effect over $300 billion admitted by Japan, probably more than that, perhaps $500 billion in damage. The most expensive disaster that is sometimes called a natural disaster, but although the tsunami was natural, the disaster was not. And the main reason it was so expensive is that this tsunami hit an area with one of the largest nuclear power plants in the world. And here are the executives from the Japanese nuclear industry on trial for the failures they had in designing this nuclear reactor. So this is called the Fukushima Daiichi nuclear plant. Nuclear plants are very good when they work, but they also present a very great potential hazard. And there are standard procedures that are used worldwide by the engineering community to deal with the potential hazard. And this was done according to international standards for the Fukushima Daiichi nuclear plant. So here's what was done. There is an assessment of the risk of the earthquake that is done by probability theory. This is done with the chances of an earthquake over some particular time period. And that time period is often it's desired that the potential for a super damaging earthquake be as rare as an event that would only occur once in 1,000 years. And because it would be impossible to engineer for the greatest possible earthquake, they tend to try to use probability theory. And they also estimate what they feel is the probable largest earthquake that could occur. And then they use a computer model to simulate how the earthquake would produce this seismic sea wave called the tsunami. And they propagate this tsunami with more computer modeling across the seafloor, predicting the time when it would arrive and the magnitude that it would have at the location where the nuclear plant is located. This analysis predicted a 5-meter high wave that would hit where the nuclear plant was located. And the engineers added a factor of safety of 0.7 meters to the height of the seawall. The seawall was hit by a tsunami on March 11th, 2011, and the tsunami was 15 meters high. 15 meters. This is what caused the disaster. And here's the thing that probably no one here knows about, that there was a geological study published in 2001, 10 years before this event, and it showed that a similar size tsunami occurred in the year 869 Common Era, about 1,000 years ago. In other words, that size tsunami had actually happened 1,000 years before. This geological report was given to Tokyo Power and Electric, but they believed their analysis that I just went through above, and they didn't take precaution for the geological evidence. I went to where that evidence was found in the Sendai Plain. Here's what the evidence looks like. This area shows where the tsunami is coming across the plain, and here is a pit cut into the rice fields that are cut across by the 2011 tsunami. And you can see the dark layers are soil, but there are these white layers. The white layers are marine shells that occur along the coast. They were carried inland by ancient tsunamis. And it's possible to date them, but there was also a historical record that showed the exact date of the most recent big tsunami that went several kilometers inland across this plain. That's why they know it was 869. And this is the scientific paper. And you can see at the top, published in 2001, 10 years before the event. Now, you might ask, why might that affect India? In 2004, there was a tsunami in the Indian Ocean. Its epicenter, where the earthquake was that generated it, was near the northern western part of Sumatra. And a city there called Aceh was very badly inundated by it. But the tsunami effects went all around the Indian Ocean. 15,000 people in India were killed by this tsunami, which was viewed as unprecedented, as something that had never happened before. That's wrong. There's a geological set of strata that was studied in northern Sumatra that found 11 prehistoric tsunamis occurring over the past, within the past 10,000 years. So these giant events, just like the big floods on Mars and the ones in the northwestern US, they leave evidence of their occurrence. And this evidence is not being utilized as much as it should to study the possibility of major disasters. There's even a whole line of criticism of the whole probabilistic based theory that is utilized in engineering to design protective works against flooding, tsunami hazards, and other kinds of extreme hazards. This is a well-known book called The Black Swan by Nassim Taleb. And it points out that there's something fundamentally wrong in our reliance upon this idea that we can model how nature really works. The whole idea of setting up probabilities is that there is really no certainty about what's happening in the future. And so to try to provide guidance to people about that, they utilize statistics and probability theory. But there is one certainty that does apply, and it hasn't been utilized enough in our dealing with Earth's big catastrophe. That certainty is what has happened can happen. We know it can happen because it has happened. And that is a real possibility. If that had been used for the Fukushima problem, the greatest disaster, at least in dollar damage wise, in history, would have been prevented. Fukushima was a human-caused disaster, unaware or ignoring nature's actualities. That is, saying that we can't know what these big catastrophes are, so we can only model them and think we can look at them with statistics. That is an assumption-based physical reasoning. Every model that is used is based on assumption. It utilizes mathematics to deduce or predict an outcome. But it ignores that there is geologically accessible information about the same thing that it is trying to predict. And this thinking that we can say how nature works, that we're so proud of our, physical approach, is the cause of the largest dollar damage disaster in human history. So one of the things I've learned from the study of these giant floods is that we can learn from nature herself, not from the assumptions we make to model nature. Science requires making discoveries about what there is of interest. And my whole experience in science is studying rare great floods. We learn nothing when we assume in advance that nothing can be learned. I've heard people tell me, you can't understand what a big flood would be like. That's completely wrong. When you say that, you don't look to see what it's like. So, kind of reasoning that instead of just studying little floods that we have access to, you study in the reverse. You look at the biggest floods that have occurred and you extrapolate down to the smaller floods that are more common that we have to worry about. Almost nobody does that. This was, my career was about doing that sort of thing that nobody else was doing. And all kinds of discoveries were made. There's another important point about this, and that is, at least in the United States, people who are being told about the potential of a great disaster are told that they have to worry about 100-year flood, 1,000-year flood, and all of those are just probabilistic statistical measures that they don't understand. When I was in Japan, we went to a village called Anyoshi that had the most catastrophic tsunami surge of any place in Japan. The tsunami wave was 40 meters high. It destroyed everything in this area where the harbor was, and there used to be a town. But in 2011, there was no town there. And the reason was that around the area of the harbor, there were these stones. And on these stones, written in Japanese, it said that a great tsunami, and it turns out it was 100 years before, came to this level. Do not build your houses below this point. People ignored what their government told them. They believed in these stones, and they built their houses way up high on the hillside. There was no loss of life. There was only minor damage to the boats that were kept down below. So this is going back to common sense. It's not what we scientists can say about nature. It's what nature can say to us and our ability to interpret that. And for the most hazardous kinds of Earth processes, as someone who's studied the most spectacular kinds of floods that have occurred in the universe, it is best to think about what's actually happened and to view real world possibilities as opposed to unrealistic abstractions conveyed by experts who think that their law-based mathematical predictions of what should happen are what we should use. But all that what should happen is based on assumptions that we don't know are correct. We don't know those assumptions. We just think they're reasonable. And nature is under no obligation to follow our assumptions. Nature follows what nature does. So I actually, in part, inspired by my my work with giant catastrophic floods, I started to think that maybe we could develop a whole science that is based on this evidence, which we would call a sign, that is left by ancient floods. And this could be used to take us back into time before there were direct measurements by hydrological procedures like stream gauging and the like, where and even before human records, which are often not that exact, look for the natural signs or evidence of the past floods. So in a particular river channel environment, one can find sediments like the gravel bars of the channel scabland, and one can find fine-grained deposits that are deposited up to the maximum water levels, and erosion features that are created, and even scars on trees. All of these are signs of the past presence of floods. And those who don't understand the way the geological record works commonly think that, oh, these things in the past there must be missing information. Well, the greatest floods, the ones that are most problematic, are the ones that leave the records that last the longest and are actually the ones that we have the best evidence on. So in the center, you can see one of my students here looking at a sequence of fine-grained deposits that were deposited by floods on a river in Utah. So there are within a river channel, and this would be a bedrock river channel, there are multiple places where you get deposits that are indicating of the flood level, and these deposits may show you that the flood got at least a certain height. And there's also evidence that one can put together that will tell us about the ages of the floods. In other words, we can get a time sequence of the magnitudes of extreme floods. Now, this kind of work has been done in many places around the world. Over the time period since I first gave the name Paleo-flood hydrology to this subject back in 1982, these are some of the places where these kinds of paleo-flood records have been done. You can see Western US, Spain, Israel, Southern Africa, parts of Australia, and here in India. I brought this method to India in the late 1980s, and a number of colleagues have pursued that. Another place where this is done extensively is in China. This was done somewhat independently of me, although in recent years, I've had students from China who've come to work with me on that topic. So you all are familiar with India's rivers up in the upper left. And I've already mentioned that the Southern Asia big rivers, like the Indus, the Ganges, the Ganga, the Brahmaputra, which has multiple names as it goes through different countries, all have impacts from giant floods that are associated with the big mountain ranges, the Himalaya and the Tibetan Plateau. But the rivers I worked on were these rivers in the peninsula part of India, and these are particularly susceptible to giant floods. Many of the biggest floods for certain size drainage basins are associated with tropical storms. The tropical storms that we call hurricanes out in the area near the United States, they get initiated in zones shown in blue, and they tend to follow patterns shown in the blue arrows. India is kind of a special condition because there are tropical storms that get initiated in the Bay of Bengal and in the Arabian Sea. And these storms can move into India, and they actually can move down the river basins. So the ones coming from the Arabian Sea can hit the headwaters of the Krishna and the Godavari. But the river that I and my colleagues studied a lot was the Narmada, because that had, for its drainage area, which is a long, narrow drainage area, the greatest floods for that drainage size in the world. And that is because the tropical storms can come off the Bay of Bengal, they hit the upper Narmada, and they move right across, and the flood wave just gets larger and larger as it goes down the Narmada River. So here's a sequence of the flood deposits in the Narmada, and over on the right shows detailed analysis of those flood deposits. One of my colleagues here, Sheila Mishra, is shown there, and we published a paper on this some time ago in Geological Society of India, where here's the sequence of flood deposits. Here's the radiocarbon dates that were done and some of the details in that stratigraphic sequence, which is shown over there. So the spectacular flood damages that we are seeing around the world sometimes get called unprecedented. Politicians who don't want to be blamed for things that go wrong, like disasters, are often wanting to blame these on nature and claiming that there's no way we could have known there was such an event. Well, politicians aren't really good at understanding the world, and they tend to make things up sometimes. So even in a lot of conventional flood hydrology, there's unrealistic extrapolation done from small common floods to what are thought to be unknown extremes. And then the other method that's used that I've talked about before is theoretical models, where the actual details of the causative processes are not as well understood as they should be. All of this is being exacerbated by climate change. Regardless of what politicians say about it, climate change is happening. And one of the things that's happening is extremes of temperature, drought, and flooding. Regardless of the politicians, we will have to deal with these realities. How will we prepare for them? Official government policy, at least in my country, will be talking about things like 100-year floods, 1,000-year floods. The general public doesn't know what these mean. And even the scientists aren't certain about what all these probabilities have to do. However, listening to nature, looking at the common signs of flooding, realizing that nature provides the certainty of what has happened can happen, that can be understood. It can be recognized that the things that will happen as certain kinds of extremes occur in the future are not unprecedented. They will have occurred before. We can just work at figuring out what we should do about them instead of thinking that we are prepared because of what people have done with what is being said about science. So this is not just a problem in how we do the science, it's how we communicate about the science. The whole idea of 100-year flood, 1,000-year flood is a failure in communicating hazard. It is associated with the biggest disaster of recent history in dollar damages, the Fukushima Daiichi one that I talked about. That has failed. So I think there is a a hubris of thinking that the future can be predicted. And it's not possible to have a prophecy. Science works best in providing guidance. The only absolute certainty that is what nature itself does. And nature isn't hiding from us. It doesn't lie to us. Nature doesn't make mistakes. So, in my view, it is a responsibility of hydrologists like myself to report what nature is telling us. And this has the byproduct of being a better way to communicate to the public about the nature of the hazard. So I thank you for giving me the opportunity to talk about my favorite subject, really big floods. And if I haven't caused you to have some questions, then I probably haven't done what I should have with my talk. Thank you.
Yeah. Thank you, Professor Becker, for the excellent lecture. I know it's almost near to midnight in US. So I will take few questions now in the YouTube chat. Mr. Sahajpal Singh, he has asked, nomenclature like valleys and channels are used widely when we talk about ancient Martian hydrology. So what is the difference between valley networks and the outflow channels on Mars?
That was something that we noticed very early when we started getting the first images of Mars. And as you know, on Earth, we have landscapes with valleys. If I can show a slide again, and this is this area of the channeled scabland, and you see these little lines here. These are streams that were dissecting this loess-covered landscape in eastern Washington. And they were in valleys. But the catastrophic flooding, which came from a glacier outburst, filled the valleys until they spilled out over divides from one valley to the next. And what had been valleys were changed into channels. This is this is the reverse of what we usually think. We usually think, well, a valley, a spectacular example would be the Grand Canyon in my home state of Arizona. It's a big valley. It's 1.6 kilometers deep, the valley. And there is a river at the bottom of it called the Colorado River. And we know that Colorado River over a few million years has carved the valley. And so the valley is big, but it's the result of a couple million years of river action. In this catastrophic flood channel, and this is what would have happened on Mars, the channels are incredibly big. They're bigger than the valleys. What happened was that another source of water came in and produced the channel. The channel is the area inundated by the water. So it is a trough, and the trough had water filling it to the edges of the trough. In a valley, you have a big, it might be not a trough, it could be a V-shaped cavity, but the river is at the bottom, and there's a little channel that is associated with that river. So this is a kind of inversion of what you think. But getting back to Mars, Mars has both kinds of features. It has valley networks that are valleys. They formed about 4 billion years ago. And they were probably associated with rainfall that was occurring on the surface of Mars at that time. The big outflow channels, something happened in Mars history that produced a phase when we had these huge floods of water coming out from the subsurface. And those are the channels, the outflow channels. So there are both kinds of features on Mars. And if I was going to give a talk on Mars, I would have a lot more slides that would tell you, show you examples of valley networks versus big outflow channels. But that's another talk.
Thank you, Professor. And then one more question we have. Can we get the ideas about the hypothesized northern ocean of Mars by studying the mega floods? And what should be the ideal approach to deal with this question?
Okay, the Northern Plains Ocean, called Oceanus Borealis, that was actually named in a paper that I did in 1991 in the journal Nature, and it was named by my colleague Bob Strom as Oceanus Borealis. This has been a controversial idea for a very long time because today Mars is a very cold, dry planet with very little evidence of water on the surface. What water is there on the surface is ice. And we are discovering more and more of that water. But in the ancient past, there was this period with much more water. We tend to think of the amount of water in terms of what's called a global equivalent layer, a GEL. That would be the depth of water that would be spread evenly over the whole surface of water of Mars. The amount of water that we have directly measured in terms of ice that is in the polar caps and also ice that is in buried ice at lower latitudes that have been measured by radars, satellite radars that penetrate, is on the order of 20 meters of global equivalent layer. The Northern Plains Ocean would have hundreds of meters of water, and that has been very controversial. I don't have time, and there would be another lecture, but
Yes.
I can basically say that incredible evidence, new evidence, has been produced that is showing the presence of this Northern Plains Ocean much more powerfully than it was done before. Some of this evidence has not received the attention it should. The Chinese mission that had the Zhurong lander landed in the Northern Plains Ocean basin. This mission had a rover, and the rover had a ground penetrating radar. The radar showed that the surface was probably sedimentary rocks, and these sediments were consistent with what they thought were fluvial sediments that had been placed on the Northern Plains. Another paper that I reviewed and didn't get accepted in a Western journal, but was published in the Chinese Academy of Sciences journal, basically imaged sedimentary rocks that had been thrown out of impact craters and argued that these sedimentary rocks were marine sediments because the Zhurong lander was about 400 meters in elevation below the high water mark of the Northern Plains Ocean. There is much other evidence that is also lining up with this past evidence of the Northern Plains water body. But I again, like the Valley Networks, this would take another talk, and
Yes.
it's something that I can't explain it in a short period
Yes.
of time.
So we'll take one more time from you to exclusively delve into the topic of Mars and its paleo flood hydrology. So
Yes.
then we have one more question. don't you think that relying on point-based geological measurements increases the risk of assessment more than the measurements and simulation-based broader approach for the floods?
Um, what did it increase? I didn't quite get.
The point-based geological measurements increases the risk of assessment more than the measurement and simulation-based broader approach. I think they are asking about this floods, the terrestrial floods, what we do in our Earth. Like you said, 100 year is the standard. So
Yeah, these standards like 100-year flood, 1,000-year floods are statistical inference that is generated by data sets that are usually conventional measures. So the time frame over which those data sets operate will be the time frame where most likely one is going to see small floods. And if you get a very big flood, this is called an outlier. And outliers don't get handled well because statistics works best when you have large numbers of things that are caused by the same process. One problem with the analysis that's done is it often just calls these things floods. Well, big floods are caused by different things than little floods. And so when you're doing the statistics, you're not doing the statistics of beans and jars. You're doing beans and baseballs and basketballs and you're doing statistics violating the principles that are needed to have a valid statistical analysis. And the biggest problem is when you're trying to see what the big rare event is. So the geological approach is that the big rare events over the past 10,000 years, we can find evidence of those. And ignoring that evidence is scientifically indefensible. To think that we can say what really big floods are like based on studying small floods is like saying, well, we're going to study mice and figure out what these strange things we don't understand called elephants are. Sorry, but this is a fundamental problem about the nature of our assumptions that we make in regard to really big floods. And of course, I'm biased towards studying really big floods.
yeah. So I think the other questions are correlated to that one only. That for engineering design we can consider worst case scenario. However, with all base decision making, it could be a point where nothing could be built, as the worst case scenario might suggest human life on Earth could eventually become extinct. So that is the extreme end of the.
Yes, yes, but the engineer is really good on working with the limitations to come up with a solution.
Yeah.
But the good engineer knows that that solution has limitations. And the public can be misled, not necessarily by the engineer, but maybe by the politician, that this dam will, this levee protects them against floods. But that is an untruth. The truth is the dam protects the people against little floods. If there is a really big flood, everything is about saving the dam and the water is passed by it. Because if the dam fails, you will have a bigger flood than nature would have produced in that location. The public is never told that. And that is a reality that is a big concern. In the United States, we have many old dams that are more dangerous than other dams. And there's a whole lot of work that I've been involved in trying to figure out which dams are the most dangerous because it's not easy to fix them all. And how do you know that when you have based everything on the thought that this dam is going to protect against all floods? You have to know what the really big floods are. So this is not a simple question, and there's many aspects of it that, again, we could have another whole set of talks about this particular problem.
Yes. So I think in India also we have more than 5,000 dams, and most were built after 1947. And we have one national project known as DRIP. So that looks into the health of the dams and these kind of scenarios when you open all the gates of the dam to protect the dam or there is a dam breach. So I think some work is being done, but then again, the worst case flood, we may not be able to protect them all. So I think that's all for today. There is no question further. So I really thank from my bottom of heart and all the members, and apologies for the delay, the technical delay which happened earlier. I know it's almost midnight in US. I thank Professor Baker, and for our members, this edited version of this lecture will be available for you to see in YouTube later on also. And Professor Baker, later in a year, we would again request you. We have this National Space Day activities also coming up during us time. So if the time permits and your health and all the this sequence permits, then we can have one more lecture from you. And we
Okay.
also invite you for in person. There is a International Association of Hydrological Science (IHS) conference is happening in IIT Roorkee in October. So, sir, if possible, sir, we'll be able to meet you and listen to you in person at IIT Roorkee also.
Okay, thank you. If
Yeah.
you do have a YouTube connection, let me know about that. I tend to collect those
Yes.
if that's available. So just send me the link.
Yes, I will edit it because initially part we have to edit.
Yeah.
Yeah.
Okay.
Thank you,
Very good.
Professor.
Thank you very much.
Thank you, Professor Baker. Thank you very much for such a wonderful lecture you have given to us. In fact, many things, first time I'm hearing from such a eminent expert and eminent scientist. Thank you, sir. Thank you very much.
Yeah.
Okay.
Thank you, Dr. S.P. Agarwal, for bearing with us. Some delay, but your lecture has more than covered the initial delays.
Okay.
Yeah.
Good
Thank you.
enough. Yeah.
Thank you. Professor.
Okay. Have a good day.
Yeah.
Good
Thank you.
night from here.
Good night.
Bye.
Next time, sit down.